Before electricity became a measured quantity, before wires, switches, batteries, and power stations entered human life, the idea of electrical force lived in a fog of wonder, superstition, and fragmented observation. For centuries, people encountered electrical effects without understanding their nature, much like hearing thunder without knowing the physics of storms. The scientific world into which Alessandro Volta was born was one where electricity existed as a curiosity rather than a controllable phenomenon, a realm of sparks, shocks, and strange attractions that hinted at hidden laws but revealed none clearly. The earliest known encounters with electrical effects came from simple natural observations. Ancient civilizations noticed that amber, when rubbed with cloth, could attract small bits of straw or dust. This phenomenon fascinated Greek thinkers, and the word electric itself comes from the Greek word for amber, electron. Yet for nearly 2,000 years, this observation remained an isolated curiosity. It did not connect to magnetism, chemistry, or energy in any coherent framework. Electricity was not considered a force of nature in its own right, but an odd property of certain materials under special conditions. By the time Europe entered the Renaissance, natural philosophy had begun to move away from purely philosophical speculation toward experimentation. However, electricity still resisted explanation. Scientists could generate static electricity using friction machines, spinning glass globes or rods and rubbing them with cloth. These devices produced visible sparks and mild shocks, enough to amaze audiences and entertain royal courts, but not enough to build reliable scientific knowledge. The electricity vanished as quickly as it appeared, leaving no steady source to study. One of the major limitations of early electrical science was impermanence. Electricity could be created, but it could not be stored or maintained. Experiments had to be conducted quickly, before the charge dissipated into the air. This made precise measurement nearly impossible. Without sustained current, scientists could not observe long-term effects, test chemical changes, or power mechanical devices. Electricity remained a fleeting visitor, never staying long enough to be fully understood. Another obstacle was the lack of conceptual language. Scientists struggled to describe what electricity actually was. Some believed it was a fluid that flowed through materials, while others thought it was a vibration or a kind of invisible fire. Competing theories existed side by side, often based more on philosophical preference than experimental proof. Terms like positive and negative charge did not yet have the clear meaning they would later acquire. Even the idea of current, a continuous flow of electric charge, did not exist as a concept. The scientific tools of the time also imposed strict limits. Instruments for measuring electrical effects were crude and unreliable. Early electroscopes could detect the presence of charge, but not quantify it accurately. There was no standard unit for electrical measurement, no consistent way to compare one experiment to another. This meant that discoveries were often difficult to reproduce, and disagreements between scientists were common. Electricity also occupied a strange place between science and spectacle. Public demonstrations of electrical phenomena became popular in the 18th century. Experimenters would shock volunteers, light alcohol vapors with sparks, or send electrical charges through chains of people holding hands. These performances amazed audiences, but often distracted from deeper scientific inquiry. Electricity became associated with entertainment and novelty rather than serious investigation. At the same time, electricity was entangled with medical speculation. Some physicians believed electrical shocks could cure diseases, revive the dead, or restore lost vitality. Electrical treatments were applied to patients with little understanding of their effects. While some benefits may have occurred, many claims were exaggerated or unfounded. This further blurred the line between scientific research and pseudoscience, making it harder for electricity to gain respect as a legitimate field of study. The relationship between electricity and magnetism was another unresolved mystery. Magnets had been known and used for navigation for centuries, yet their connection to electrical effects remained hidden. Some scientists suspected a link, but no experimental evidence could confirm it. Electricity and magnetism were treated as separate phenomena, studied by different methods and described using different theories. The unification of these forces lay far in the future. Natural electricity, such as lightning, added to the confusion. Lightning was powerful, destructive, and unpredictable, far beyond the weak sparks produced in laboratories. Some believed lightning was divine in origin, a sign of supernatural forces at work. Others suspected it was electrical in nature, but could not prove it convincingly. Even after experiments suggested a connection, the vast difference in scale made it difficult to accept that the same force caused both lightning bolts and tiny laboratory sparks. The social structure of science also shaped the understanding of electricity. Scientific communication was slow and fragmented. Experiments were shared through letters, private demonstrations, or limited publications. Misinterpretations spread easily, and replication was rare. National rivalries and personal pride sometimes interfered with objective evaluation of results. In this environment, progress depended heavily on individual insight and persistence rather than systematic collaboration. By the mid-18th century, electricity had reached a turning point, but it was still incomplete and unstable as a field of knowledge. Scientists knew how to generate static charges and observe their effects, but they did not know how to control electricity in a continuous way. They lacked a reliable source of power, a method to sustain electrical flow over time. Without this, electricity could not be fully explored or applied. This was the intellectual climate into which Alessandro Volta entered. He inherited a world rich in observations but poor in explanations, full of experimental hints but lacking a unifying principle. Electricity stood on the edge of transformation, waiting for a breakthrough that would convert it from an intermittent curiosity into a dependable force of nature. The stage was set for a shift from spectacle to science, from momentary sparks to continuous current. What made this period especially significant was that the limitations themselves pointed toward the solution. The inability to sustain electricity highlighted the need for a new approach. Friction alone was not enough. Static machines had reached their limits. Scientists needed a method that could generate electricity chemically or mechanically without constant human effort. They needed electricity that could last, flow, and be measured. The absence of such a source shaped every experiment conducted at the time. Researchers worked around the problem rather than solving it, adapting their questions to what was possible instead of what was necessary. Many suspected that the key lay in the interaction between materials, but no one had yet demonstrated this clearly. The idea that different metals might produce electricity when brought into contact existed only as a vague speculation. Thus, the scientific world before electricity was understood was not ignorant but incomplete. It was a landscape of partial truths, brilliant guesses, and frustrating dead ends. Electricity was known but not mastered, observed but not explained, admired but not controlled. This fragile foundation made the coming breakthrough not only possible but inevitable. When the right insight arrived, it would not merely add a new fact to science. It would reorganize the entire understanding of electrical phenomena. In this sense, the world before Volta was a world waiting for continuity instead of interruption, waiting for measurement instead of spectacle, waiting for a simple idea that would turn scattered sparks into a steady stream. The mystery of electricity was not solved because the question had not yet been fully formed. Once it was, the transformation of science would begin. Curiosity is often born from disagreement, and in the life of Alessandro Volta, scientific rivalry became the spark that pushed electricity toward clarity. The second keynote centers on how Volta's questioning mind and his intellectual conflict with other thinkers, especially Luigi Galvani, reshaped the direction of electrical science. This was not a rivalry driven by ego alone, but by fundamentally different interpretations of nature, and it unfolded at a time when the boundaries between biology, physics, and chemistry were still blurred. Volta was deeply curious, but his curiosity was disciplined. He did not accept explanations simply because they were popular or emotionally appealing. He demanded mechanisms, causes that could be isolated, tested, and repeated. This mindset placed him at odds with Galvani, a respected physician and anatomist, whose experiments in the 1780s appeared to show that electricity was generated by living tissue. Galvani observed that the legs of dead frogs twitched when touched with metal instruments, especially when two different metals were involved. To Galvani, this was evidence of an intrinsic animal electricity, a vital force stored within muscles and nerves. The idea was captivating. It seemed to connect electricity to life itself, offering a bridge between physics and biology. Many scientists were drawn to it because it suggested that electricity might be the secret force animating living beings. In an age still influenced by vitalism, the belief that life was governed by special forces beyond physical laws, Galvani's interpretation felt natural and even poetic. Volta, however, saw something different. He did not deny the experimental observations. The frog legs clearly moved. But he questioned the explanation. He noticed that the twitching depended on the presence of metals, particularly when two dissimilar metals were used together. To Volta, this suggested that the source of the electricity might not be the animal tissue at all, but the interaction between the metals themselves. This distinction was subtle but revolutionary. Rather than dismissing Galvani outright, Volta began a systematic investigation. He repeated the experiments, modified them, and removed biological components wherever possible. He tested metals in contact without frog tissue and observed electrical effects. He varied materials, shapes, and arrangements, carefully noting which combinations produced stronger responses. This methodical approach reflected Volta's belief that nature could be understood through isolation of variables, not through metaphor or assumption. As Volta's experiments progressed, the rivalry deepened. Galvani and his supporters defended the idea of animal electricity, refining their arguments and conducting their own tests. Scientific debate became intense, sometimes personal, but it remained rooted in experimentation. Letters, papers, and demonstrations circulated across Europe, drawing other scientists into the discussion. What might have remained a narrow dispute instead became a catalyst for broader inquiry. Volta's greatest insight during this period was recognizing that contact between different metals could produce a continuous electrical effect. He began arranging metals in series, observing that the electrical influence increased with the number of contacts. This was a crucial departure from the prevailing focus on static electricity. Instead of generating charge through friction, Volta was uncovering a new principle. electricity arising from material interaction. His curiosity pushed him beyond the immediate debate. He asked questions that extended past the frog experiments. If metals could generate electricity, could this effect be sustained? Could it be amplified? Could it be controlled? These questions led him to experiment with stacks, chains, and arrangements that hinted at the possibility of a steady current. In pursuing these ideas, Volta was not merely trying to win an argument. He was trying to understand the underlying structure of electrical phenomena. The rivalry also shaped Volta's communication style. He was careful in how he presented his conclusions, emphasizing experimental evidence rather than attacking Galvani's character or competence. He acknowledged the value of Galvani's observations while firmly rejecting the interpretation. This balance helped Volta to gain credibility and ensured that the debate advanced knowledge rather than collapsing into hostility. At the same time, the conflict forced Volta to sharpen his reasoning. He had to anticipate objections, design experiments that could not easily be dismissed, and demonstrate that electrical effects could exist independently of living tissue. In this way, rivalry became a refining tool. It exposed weaknesses, demanded rigor, and pushed ideas toward greater precision. The broader scientific community benefited immensely from this tension. The debate drew attention to electricity as a serious field of study and encouraged others to experiment with metals, circuits, and chemical interactions. It broke down artificial boundaries between disciplines, showing that electricity could not be confined to biology or physics alone. The concept of electrochemistry began to take shape, even if the term itself had not yet been coined. Volta's curiosity also extended beyond experimentation to instrumentation. He was deeply interested in creating devices that could reliably demonstrate electrical effects. He understood that an idea gains power when it can be shown clearly and repeatedly. This drive to build and refine instruments laid the groundwork for his later invention of the electric battery. The rivalry with Galvani did not distract him, it focused him. Emotionally, the conflict tested Volta's resilience. Challenging a respected figure meant risking reputation and isolation. Yet Volta remained confident in his evidence. His commitment to empirical truth over popular appeal revealed a core aspect of his character. He was willing to stand alone if the data demanded it. Over time, the scientific tide began to turn. Experiments increasingly supported Volta's interpretation that electricity arose from the contact of dissimilar metals rather than from animal tissue. While Galvani's contributions were not dismissed, their meaning was reinterpreted. The frog legs did not generate electricity, they merely responded to it. This shift in understanding marked a decisive moment in the history of science. The rivalry between Volta and Galvani thus became more than a personal dispute. It represented a transition from speculative explanations rooted in life forces to a more mechanistic, material-based understanding of nature. Volta's curiosity transformed disagreement into discovery, turning a puzzling biological observation into the foundation of electrical technology. In the end, Volta's greatest victory was not proving someone else wrong, but revealing a deeper truth. His curiosity, sharpened by rivalry, dismantled old assumptions and opened a path toward controlled, continuous electricity. The debate that began with twitching frog legs ended by illuminating the hidden power of metals, setting the stage for one of the most transformative inventions in human history. The invention of the first electric battery did not arrive as a sudden stroke of genius, but as the quiet outcome of years of observation, patience, and careful reasoning. Alessandro Volta's breakthrough was rooted in his desire to create a source of electricity that did not vanish in an instant, a source that could be relied upon, studied, and repeated. At the time, electricity remained fragile and momentary, appearing as sparks or shocks and disappearing before its nature could be fully examined. Volta understood that without continuity, true understanding would remain out of reach. His experiments with metals gradually revealed a pattern. When two different metals came into contact, an electrical effect appeared. When those metals were separated by a moist material, the effect became stronger and more consistent. Volta realized that moisture played a crucial role, not as a living substance, but as a conductor that allowed interaction between metals. This insight led him to explore combinations of metals and electrolytes with increasing precision. Volta tested countless arrangements, stacking metals in various sequences, changing their order, size, and spacing. He observed that zinc and copper produced particularly strong effects when paired together. Rather than focusing on a single contact point, he began to imagine a chain of interactions, each one adding to the total electrical output. This idea of accumulation was revolutionary. It suggested that electricity could be built up step by step, rather than generated all at once. The decisive moment came when Volta arranged alternating disks of zinc and copper, separated by cloth soaked in salt water. This simple structure produced something unprecedented, a steady, continuous flow of electricity. Unlike static charges, this current did not dissipate immediately. It persisted as long as the arrangement remained intact. For the first time in history, electricity could be sustained. This device, later known as the Voltaic Pile, marked a fundamental shift in science. It transformed electricity from a fleeting phenomenon into a controllable resource. Researchers could now conduct experiments that required time, observe gradual changes, and repeat tests under similar conditions. Measurement became possible, comparison became meaningful, electricity entered the realm of quantitative science. The battery also revealed a deeper connection between electricity and chemistry. Volta did not fully understand the chemical reactions occurring within his pile, but he recognized that chemical interaction was central to its operation. This realization opened an entirely new field of inquiry. Scientists soon discovered that electrical currents could drive chemical reactions, decompose substances, and reveal the internal structure of matter. The battery became a tool for exploring the unseen. What made Volta's invention especially powerful was its simplicity. It did not rely on complex machinery or rare materials. Zinc, copper, salt water, and cloth were readily available. This meant that scientists across Europe could replicate the device with relative ease. The Voltaic Pile spread rapidly, accelerating discovery and collaboration. Knowledge no longer depended on unique instruments locked away in elite laboratories. The impact of the battery extended beyond science into society itself. It changed how people thought about energy. Electricity was no longer an unpredictable curiosity. It was a source of power that could be harnessed. This shift laid the conceptual groundwork for future technologies, even those Volta could not have imagined. Every electrical device that requires stored or continuous energy traces its lineage back to this invention. Volta's battery also reshaped scientific methodology. Experiments could now be designed around cause and effect rather than chance. Researchers could isolate variables, test hypotheses, and build upon previous results. The battery became a standard reference point, allowing discoveries to accumulate rather than reset with each experiment. Science gained momentum. The invention challenged existing theories as well. Many scientists initially struggled to reconcile continuous electrical flow with older models based on static charges. The battery forced a reevaluation of what electricity was and how it behaved. Concepts such as current, voltage, and resistance would eventually emerge from efforts to explain the battery's operation. Volta's invention did not just answer questions, it created new ones. Personally, Volta approached his success with restraint. He did not exaggerate his claims or present his invention as a final answer. He understood it as a beginning, a tool for others to use and improve. This humility contributed to the battery's acceptance and integration into scientific practice. Volta had provided a foundation, not a closed system. The Voltaic Pile also symbolized a philosophical shift. It demonstrated that natural forces could be understood through material interactions, rather than mysterious life forces or metaphysical principles. Electricity emerged as a universal phenomenon governed by physical laws. This perspective aligned with the broader movement toward modern science, where explanation replaced speculation. In retrospect, the invention of the electric battery stands as one of the defining moments in scientific history. It bridged gaps between disciplines, transformed experimental practice, and reshaped humanity's relationship with energy. Volta's achievement was not merely technical, it was conceptual. He showed that persistence, curiosity, and careful reasoning could turn an elusive mystery into a dependable reality. The steady current produced by the Voltaic pile was more than an electrical flow. It was a flow of possibility, carrying science into a new era. From that quiet stack of metal and cloth emerged a world powered by electricity, a world that continues to build upon Volta's simple, profound insight. The transformation of science and technology that followed Alessandro Volta's work did not happen overnight, but once the door was opened, it could never be closed again. The ability to generate a continuous electric current altered the direction of human understanding in ways that reached far beyond Volta's own experiments. What had once been a scientific curiosity became a foundational force, reshaping laboratories, industries, and eventually everyday life. Before Volta's battery, scientific investigation into electricity was constrained by time and chance. Experiments had to be rushed, observations were incomplete, and results were often inconsistent. With the arrival of a steady current, researchers could slow down, observe carefully, and repeat procedures under controlled conditions. This alone transformed the nature of experimental science. Electricity could now be treated like heat or motion, as a phenomenon that could be measured, regulated, and analyzed systematically. One of the earliest and most profound impacts was in chemistry. Scientists quickly discovered that electric currents could break compounds into their constituent elements. This process, later known as electrolysis, revealed that substances previously thought to be indivisible were in fact composed of simpler parts. Water, for example, could be separated into hydrogen and oxygen using electrical current. This insight fundamentally changed chemical theory and led to the identification of new elements. The battery also enabled the exploration of the relationship between electricity and magnetism. Continuous current made it possible to observe magnetic effects over time rather than in brief flashes. Eventually, this led to the realization that electric currents produce magnetic fields, a discovery that would culminate in the unification of electromagnetism. Without Volta's invention, such experiments would have been impossible or severely limited. Technology soon followed science. The battery provided a portable source of power, allowing devices to operate independently of static machines or natural phenomena. Early electrical instruments, telegraph systems, and experimental motors all depended on stored or continuous electrical energy. These technologies laid the groundwork for global communication and mechanization, reshaping societies and economies. The influence of Volta's work extended into education and scientific culture. Laboratories began to standardize experiments around electrical current. Students could learn by doing, replicating established procedures rather than merely observing demonstrations. This shift encouraged a more democratic and collaborative scientific environment, where knowledge could be shared and expanded collectively. Industrial innovation accelerated as electricity became more predictable. Processes that relied on chemical reactions or precise control benefited directly from electrical power. Over time, batteries evolved, power generation expanded, and electrical grids emerged. While these developments occurred long after Volta's lifetime, they were conceptually rooted in his demonstration that electricity could be generated continuously and reliably. The social implications were equally significant. Electricity changed how people lived, worked, and communicated. Night was no longer defined by darkness, distance by isolation, or labor by physical strength alone. Though Volta could not foresee electric lighting, computers, or digital communication, his work made them possible by establishing electricity as a controllable resource. Volta's legacy also reshaped scientific thinking itself. His success demonstrated the power of experimental evidence over speculation. It showed that complex phenomena could be understood through simple, well-designed experiments. This reinforced a culture of inquiry that valued precision, replication, and openness to revision. In recognizing Volta's contribution, the scientific community honored him by naming the unit of electric potential the volt. This gesture symbolized more than respect. It acknowledged that modern electrical science is built upon his insight. Every measurement of voltage is a quiet tribute to his work. The transformation sparked by Volta's battery continues to unfold. As technology advances, from renewable energy storage to medical devices and space exploration, the principles he uncovered remain relevant. His invention did not merely solve a problem of his time. It created a framework for progress across centuries. In reflecting on this transformation, it becomes clear that Volta's impact lies not only in what he built, but in what he enabled. By turning electricity into a stable and accessible force, he allowed humanity to explore, innovate, and connect in ways previously unimaginable. The world powered by electricity is, in many ways, the world shaped by Alessandro Volta. Alessandro Volta's legacy does not rest solely in the invention of the first electric battery, but in the enduring transformation he brought to human understanding, scientific method, and technological possibility. His influence extends far beyond the 18th and 19th centuries, quietly shaping the modern world in ways so fundamental that they are often taken for granted. To understand Volta's lasting legacy is to recognize how a single idea, grounded in careful observation and persistence, can ripple across centuries and redefine civilization itself. At the most immediate level, Volta's work permanently changed how electricity was perceived. Before him, electricity was fragile and theatrical, a phenomenon of sparks, shocks, and fleeting effects. After Volta, electricity became reliable, measurable, and controllable. This shift in perception was profound. Once a force can be controlled, it can be studied deeply. Once it can be studied deeply, it can be applied. Volta did not simply add a new device to science. He altered the status of electricity from curiosity to cornerstone. One of the clearest signs of Volta's enduring influence is how deeply his ideas are embedded in scientific language and education. The volt, the unit of electric potential, ensures that his name is spoken daily in classrooms, laboratories, hospitals, factories, and power stations around the world. This is not symbolic alone. It reflects the reality that modern electrical systems are built on the conceptual framework that began with his experiments. Every time voltage is measured, regulated, or optimized, Volta's intellectual presence is felt. Volta's legacy is also methodological. His approach to science emphasized careful isolation of variables, repeatable experiments, and restraint in interpretation. He demonstrated that disagreement, when guided by evidence, could lead to progress rather than division. His rivalry with Galvani did not end in dismissal or dominance, but in refinement of understanding. This model of scientific debate became a template for future inquiry, encouraging skepticism without hostility and curiosity without dogma. The battery itself became one of the most important scientific tools ever created. It enabled discoveries that Volta could not have predicted, including the identification of new chemical elements, the development of electroplating, and the foundations of electromagnetism. Michael Faraday's work on electromagnetic induction, which ultimately led to electric generators and motors, depended on the existence of sustained electric current. Without Volta's battery, the chain of discoveries leading to modern power generation might have been delayed by decades or longer. Technologically, Volta's legacy expanded as batteries evolved. From early chemical cells to modern lithium-ion batteries, the basic principle remains the same: chemical energy converted into electrical energy through controlled interaction. This continuity across centuries is remarkable. While materials have changed and efficiency has improved, the conceptual heart of battery technology still echoes Volta's original insight. Portable electronics, medical implants, electric vehicles, and renewable energy storage all trace their ancestry to his work. The social impact of this legacy is immense. Electricity has reshaped how societies organize time, labor, communication, and space. The ability to store and transport energy made industrialization more flexible and decentralized. It enabled communication across continents, powered machines that multiplied human effort, and eventually gave rise to digital technology. Though Volta lived in a world lit by candles and governed by muscle and wind, his ideas helped create a world illuminated by screens and driven by data. Volta's influence also extended into philosophy and world view. His work reinforced the idea that nature operates according to discoverable laws, not hidden vital forces accessible only through speculation. By showing that electrical phenomena could be explained through material interaction, he helped move science away from mystical explanations toward physical causation. This shift supported the broader Enlightenment movement, which emphasized reason, evidence, and human capability. In personal terms, Volta's character contributes to his legacy as much as his inventions. He was not a showman or a radical provocateur. He worked quietly, methodically, and with humility. He accepted recognition without seeking spectacle, and he framed his discoveries as contributions rather than conclusions. This attitude helped integrate his work smoothly into scientific practice, ensuring that it would be built upon rather than resisted. Recognition during his lifetime confirmed his importance. Volta was honored by scientific institutions and even by political leaders, including Napoleon Bonaparte, who recognized the strategic and symbolic value of scientific advancement. Yet Volta never became defined by power or politics. his loyalty remained with inquiry itself. This separation between scientific contribution and personal ambition strengthened the credibility of his work and preserved its influence across changing political landscapes. The endurance of Volta's legacy is also evident in how adaptable it has proven to be. As scientific understanding deepened, new theories explained the chemical and physical processes underlying battery operation. Volta's original explanations were refined, corrected, and expanded, but his core insight remained intact. This adaptability is a hallmark of great scientific contributions. They do not collapse when new knowledge emerges. They provide a framework within which new knowledge can grow. In education, Volta's story continues to inspire. He represents the power of patience, the importance of questioning assumptions, and the value of experimental evidence. His journey shows that transformative discoveries often arise not from sudden inspiration, but from sustained attention to small details others overlook. For students and researchers alike, Volta's life offers a model of how curiosity, when paired with discipline, can change the world. Looking at the modern era, Volta's legacy intersects with some of humanity's greatest challenges. Energy storage is central to the transition toward renewable power sources. Batteries are essential for stabilizing solar and wind energy, reducing reliance on fossil fuels, and addressing climate change. In this context, Volta's original invention takes on renewed significance. The future of sustainable energy still depends on principles he helped establish more than 2 centuries ago. Even in fields far removed from classical physics, Volta's influence persists. Medical technologies rely on batteries to power life, saving devices. Space exploration depends on stored electrical energy to operate far from Earth. Communication networks, from mobile phones to satellites, are sustained by electrical systems rooted in the concept of continuous current. Volta's legacy thus extends into the most advanced frontiers of human activity. Ultimately, Alessandro Volta's lasting legacy lies in empowerment. He empowered science with a tool that made deeper understanding possible. He empowered technology with a reliable source of energy. He empowered society by unlocking a force that could be shaped to human purpose. His contribution reminds us that progress often begins with making the invisible reliable, turning mystery into method. Volta did not set out to change the world in grand terms. He sought clarity, consistency, and truth. Yet by achieving those goals in a single domain, he altered the trajectory of many others. The modern world, humming quietly with electrical current, stands as a living testament to his work. In every stored charge, every measured voltage, and every device brought to life by electricity, Alessandro Volta's legacy endures.